Good evening. This is a public review of Dr. Kim's lecture on Motional EMF. I hope you find it helpful in better understanding Motional EMF and some of its common day applications. Let's imagine a bar in an area of magnetic field coming through a page. On the metal bar, a mobile sea of electrons have been drawn in blue and positive holes in red. As we know, magnetic fields are created by moving charges, and magnetic forces only act on mobile charges. Once we give the bar a push to the left, we can solve for the magnetic forces experienced by individual charges by the magnetic field. Each individual charge feels a force that is the cross product of its charge times the velocity and the magnetic field that it moves through. By the right-hand rule used with the cross product, we find that the force on positive mobile charges is upward and downwards for negative charges. Because our bar is a metal, its charges are free to move freely across the metal. With the movement and separation of the charges, a growing electric field is created. This electric field also produces a force in the opposite direction of the magnetic field. When the metal has reached equilibrium, the electric force that has been created due to the separation of charges is equal in magnitude but opposite in direction to the magnetic force. Thus, the net force on the mobile charges is zero. We can set the magnitudes of the forces equal to each other and deduce an important relationship between E and B. So important that we'll save it at the bottom of our screen for later. Now let's take our polarized bar and imagine it was sliding along frictionless rails. This keeps the bar moving at a constant speed. But let's also connect the bars with a resistor on the right side. The moving bar acts as a battery with positive end by the positive charges and its negative charges near the negative end. The EMF of the battery is the same as in any circuit, equal to the electric field times the length of the circuit. Remember the relationship between the electric field and the magnetic field we stated at the bottom of the screen? This is where it can be handy. The EMF of the battery is equal to the velocity of the bar times the length of the bar and the magnetic field through which it moves. This relationship is really important later, so we'll also save it at the bottom of the screen. We have a battery connected to a resistor. Sounds like a circuit. It's very similar. We can imagine the bar or battery connected to this resistor in a circuit, with a very real conventional current flowing clockwise down the resistor and back up through the metal bar. Because we have now established a current, we also have to consider the force created by the current along a wire or the bar of length L and moving through a magnetic field B. Given by the right-hand rule, the entire wire or bar experiences a force to the right. Our bar once moved at a constant speed due to the lack of friction force created in the rails, but a force to the right, opposite in direction in which our bar travels, will slow down the motion of our bar. We will save this formula for force. It may help us fix this problem. In order to keep the bar moving at constant speed, polarized, the battery running, and current flowing, an equal but opposite mechanical force must be applied. If we pull the bar to the left by a mechanical force equal in magnitude but opposite in direction to the magnetic force to the right, we can recreate the constant motion of the bar and keep the current flowing. So why is motional EMF so interesting? When Dr. Kim first mentioned a bar sliding along frictionless rails, I thought of a little kid pushing his Thomas the Train car along a toy railing. These days, they've gotten so good at making these toy railings, that the trains only stop when they run off the track. But it is also how some trains operate in real life as well. Some methods of ground locomotion, like trains or roller coasters, use linear motor to propel themselves. A linear motor is an electric motor that has had its stator and rotor unrolled so that instead of producing a torque or rotation, it produces a linear force along its length. The most common mode of operation is a Lorentz-type actuator, in which the applied force is linearly proportional to the current and the magnetic field. This is very similar to the force that pushed our metal bar to the right and the mechanical force we applied to the left to keep the bar moving at constant speed.